Self-improving AI systems seek to reduce reliance on manual engineering by learning to autonomously update their own learning and problem-solving processes. The core limitation of standard self-improving architectures is their structure. They rely on a base model performing the work and a fixed, handcrafted meta-agent evaluating and updating that work. Because humans hand-coded the meta-agent, the AI can never outgrow its original evaluation parameters. The system's evolution is strictly bounded by the imagination of its engineers. The obvious solution seems to be adding a second, higher-level agent to improve the meta-agent. This simply pushes the bottleneck up a level. It creates an infinite regress, requiring a layer above the layer to keep functioning. As long as the evaluator remains a static piece of code, true, unbounded recursive self-improvement is mathematically impossible. The system will eventually hit a hard ceiling. The Darwin Gödel Machine, or DGM, provided a baseline for solving this in code generation tasks. The original DGM split the agent. One writes code, the other uses a hard-coded evaluation script. This works for coding, but on poetry or math, the fixed evaluator fails. The solution is the DGM-Hyperagent. Solver and evaluator merge into a single, unified Python program. Because the entire program is editable, the agent can access and rewrite the logic it uses to evaluate itself. This is metacognitive self-modification. The algorithm rewrites the algorithm it uses to generate future improvements. By collapsing the hierarchy into one self-referential script, the system's initial implementation can be overwritten to optimize for any computable task. The hyperagent explores solutions through an open-ended evolutionary loop. It samples parent agents probabilistically, weighting its selection heavily toward those with the highest performance scores. To prevent premature convergence on a single strategy, it applies a counterweight, inversely weighting agents that have already spawned many descendants. Every successful self-modification is saved in a progress archive, serving as a retained stepping stone for future generations. The agent cannot hallucinate its way to better performance. Every structural change to its own code must pass empirical benchmark testing to survive. We can observe this in academic paper review. This is a highly subjective task without a clean mathematical ground truth. The initial agent scores a 0 accuracy. A state-of-the-art static model, AI Scientist v2, caps out at a 0.630 accuracy. Around generation 39, the hyperagent begins attempting to improve its own performance. Its early strategies rely on attitude instructions. It edits its own system prompt to adopt a persona, commanding itself to be a rigorous and critical academic reviewer. At generation 54, the agent's performance tracking recognizes that behavioral prompting produces unstable results. It deletes the persona prompts and hard-codes a multi-stage evaluation pipeline. It forces itself to complete a specific weakness identification checklist before rendering an accept or reject decision. The agent autonomously discovered that structured logic pipelines reliably outperform prompt engineering. Next, the hyperagent is tasked with robotics reward design. The objective is to write a reward function that trains this quadruped to maximize its torso height. Human engineers and static AI typically fall into a local optimum here. They directly reward height, which teaches the robot to stand tall and remain completely stationary. The hyperagent incrementally builds an internal knowledge base, mapping the simulation's physics constraints and environment variables. Using that data, it writes a non-myopic reward function that penalizes standing still and instead incentivizes crouching and jumping to achieve a higher peak maximum height. By rewriting its own logic based on simulation feedback, the hyperagent bypasses human heuristics to find the actual mathematical optimal in a physical environment. The solutions to paper review and robotics are useful, but the real significance is how the agent modified the mechanism used to find those solutions. To evaluate its own code edits, the agent autonomously constructed cross-generation performance tracking. It wrote scripts to measure the total number of generations, map improvement trends, and monitor label distribution bias to prevent itself from falling into classification collapse. It engineered a persistent memory tool directly into its own architecture. It uses timestamps and JSON structures to log causal hypotheses between runs. If generation 55 was too harsh on its grading, the agent records that data so generation 56 avoids the exact same error. No engineer explicitly prompted the AI to build these tools. It autonomously constructed the MLOps infrastructure required to sustain its own continuous learning. This raises a critical question regarding generalization. Does a meta-agent optimized on robotics and academic papers learn anything useful for entirely unseen domains? To test this, researchers applied the agent to a new benchmark, Olympiad-level mathematical grading. They measured success using an improvement at 50 metric. This tracks the pure performance gain generated by a fixed meta-agent over exactly 50 iterations on a novel task. This bar chart displays the baselines. The initial meta-agent and a static transfer agent both achieve near zero improvement on the new math task. But the DGM-Hyperagent transfer model arrived at the math task already equipped with the persistent memory and tracking tools it engineered in previous environments. This chart reveals the result. The Hyperagent achieves a massive 0.630 performance gain, zero shot. This line plot visualizes the trajectory. The self-referential architecture creates a compounding performance curve that rapidly separates from the flat lines of static systems. DGM-Hyperagents provide a framework for AI systems to continually refine the process by which they discover and apply future improvements.